think we're ready to start, almost. Still some people coming. I hope you enjoy your lunch and feel comfortable. I hope I'm not going to bore you too much, but I'm also okay if you just get some rest after lunch. But I hope in the end you will give me some questions, because for every question I have still some spare t-shirts here, and I also got an amazing t-shirt from Eclipse with Jakarta E, so I put it on. I have my MicroProfile t-shirt below, but MicroProfile is slowly coming to the Jakarta E family, as Kevin explained yesterday in his lightning talk. So both are very close to each other. So in this talk, I'm going to talk about scalability. So let's start with the simple things. What it really means. Is it important, or is it just another buzzword? You probably heard it a lot of times during the conference, because there were many reactive talks, and part of the reactive building blocks is scalability, or I think the reactive manifesto says elastic applications, but in the end means scalable applications, because applications should adapt to the load to be able to grow when there's some more work to do, and also to shrink, to save resources if there is less work to do. So it's not a buzzword, but can we talk about highly scalable applications? Another buzzword. Very often you can see it in articles. Maybe not so much recently, because it really is a buzzword in the same way as big data is a buzzword. Like a couple of years ago, it wasn't so often, wasn't so common to have so much data, and everybody use the term just to call more than normal amount of data. Now almost everything that used to be called big data is normal, because the amount of data is growing, and we just accept it. So it's not really a buzzword, but it's a fact, and we want to adapt. And the main goal in seeking scalability is to design our applications so that they are able to grow, to adapt to the load. And how they do that? They can do that only when either they save the resources they have, so they have spare resources to use when the load increases, or more often they are able to get more resources and use more resources on the fly, on demand. This is very easy to do in the cloud environments, where you can just spin up additional instances or additional resources just by click on the button. You no longer need to buy the resources in front before you need to use them. So it's very easy to scale, but the application has to be prepared for this. It's not as straightforward as it may sound, because the application has to be able to distribute the load when it has more workers, more nodes in a distributed environment. And it comes to the same problem as we had in school with math, where we learned that just adding more workers didn't speed up the job comparably to him. Like, you can add just too many workers and expect the same reduction of time, because then the communication increases. Maybe the workers don't synchronize well with each other, and they wait until some other worker finishes their job so they can take over. And this is also in our applications. We need to design the applications so that they synchronize well. All the components should work without waiting for the other components. But still, I missed one option to scale, which is vertical scaling, which is an option you always have, because always you used to have until some physical limits were deprived us of this option. But up until some point, you could buy a more performant CPU and more memory, but there are physical limits to this. And the point is, even then, if there are limits, these things get more and more expensive. So in some way, it's much less expensive to buy hundreds of average computers than to buy one supercomputer, which is even has less power than these 100 computers together. So it's more more efficient to scale horizontally, just by adding average resources, but just multiplying them as many times as we need. But this is more complex because we need to synchronize. We get to write distributed applications. We have, as I explained, much more communications, and the communication is less reliable and slower. And we often end up with having the problem with state that we need to distribute and share across components. Because very often we used to rely on some state in memory, which was always available in monolith, because all our code was running in the same place. Now, when we when we want to have our application scalable, we have to think about this, and we have to think about distributing the information evenly across all the places where our computation happens. So one thing that can help is to adopt a microservices architecture. It's no longer a new thing, so I'm not going to go into deep details. The biggest thing, the biggest advantage you can get from microservices in this aspect is that you can create more granular applications and then scale them just by separating processing onto different machines and let them do their own job and do it well, compared to doing all the job in one computer, in one machine, in one monolith. You can also scale them separately. So if you need, for example, if I'm talking about people, if you need more people to dig in the hole and then only one person to put something into the hole, you just scale up the number of workers that dig the hole. You don't need to add both type of workers, which you would have to do if you had monolith, because you would have to scale everything. Separating components into microservices allows you to have more granularity in scaling. But again, you get more complexity because you have to think about scaling things differently and distributing the information among them, and also synchronizing them. In a monolith, you would just use Java API to synchronize threads. If you're using threads across microservices, you would have to have network communication or some shared state which you use to exchange information. The goal of MicroProfile here is to simplify the microservices part. So when you opt to use microservices, MicroProfile attempts to simplify your life by providing standard APIs, which will, for one thing, make it easier for you to develop application. For another thing, make it easy to postpone some technological decisions to a later time, because there are many implementations of the same API. So you can start developing with one implementation that is fast, easy to develop with, and later switch to another one which is more suitable for production. And you can do the decision later in time, after you have proof of concept. And there are a lot of things that MicroProfile simplifies here. It simplifies configuration API. It's a thing that is necessary everywhere, not only in microservices, but there are technologies that can help with spreading the configuration. So it's good to have a unified API, and then just spread the configuration by some hidden mechanism. But if the mechanism knows about all the microservices only consume the API. They don't need to know about the technology behind spreading the configuration. But you need something to glue the services together to distribute the information. I'm not going to talk about in detail about the rest. There's many aspects where MicroProfile can help. But what MicroProfile still misses is the glue that connects services together. It has lots of things like monitoring of distributed services, so you can implement a mechanism to find out where distributed request starts, how it goes through other microservices, and when it ends. You can secure communication among microservices, but to distribute the information, it is up to you. You either use REST calls, but then you have to route the information to the services. You have to use service discovery, or use a message broker, which is not yet part of MicroProfile, or use another mechanism. And I'm going to talk about the third option, the alternative mechanism, which is very sophisticated, but easy to use in the end. And this is in-memory data grids, and in particular distributed memory data grids, because there are also, all the data grids are distributed, but not all caches are distributed, so that's sometimes confusing. But data grids have the purpose of extending your memory and distributing your memory to multiple nodes, so that you can access the memory in the normal way that you do in one node, like with common interfaces like map and sets. But the real work is done behind the scenes, where the mechanism, the data grid, communicates across the cluster of instances and distributes the data, replicates the data, so it can provide a reliable mechanism to store data, at least as long as enough nodes in the cluster are running. So if you scale up with too many nodes, you have pretty safe storage, and it's a fast storage because it's still in memory. So you can grow beyond the limits of one node that can have gigabytes of memory, but with distributed data grids you can grow to terabytes of RAM memory, not on disk, but RAM memory, and it's very fast. And it's fast because network communication is much faster even compared to SSDs. And these distributed data grids also provide mechanisms to synchronize information. So it's not only spreading the information by having it available across the cluster, but you have distributed logs and distributed executors, so you even can send code that is executed on every node. And this is important because the data doesn't have to be on your node. So sometimes when there's too much data, it's more efficient to send the serializable code to the node where the data is. And these data grids have often the option of running queries in the distributed way. So they take your query, distribute it to every node, take results and aggregate them at your original node. Now I'm getting back to MicroProfile, where Payara Server and Payara Micro are one of several MicroProfile implementations, and they already provide Hazelcast as a distributed data grid, so it's easy to start with. You also can choose another MicroProfile implementation and bring in another Hazelcast or other distributed data grid There's also a standard API called JCache, which standardizes parts of distributed data grids, particular caching mechanism. And Payara also adds a easy-to-use messaging mechanism where you just raise CDI events, and these events are distributed. They have to be serializable, but then they are distributed to all the members of the cluster, where you can respond to the events without writing any boilerplate code. Payara Server and Payara Micro are different in only basically in packages and some portion of functionality, where Payara Micro is, unlike traditional servers, is just a jar file which you can execute on command line, and you can either add your application to it or bundle it together in an executable jar file. So it's something that you see very often in microservices, where Spring Boot also packages everything in one jar file. Now, when we have Docker environments, it's not so huge difference to have an application server and deploy application to it on startup, because from outside of the Docker container, it doesn't matter. You don't care if it's just a jar file executed in Docker or an application server, but in your custom environment, or if you're not using Docker, it may make a difference. Now, quickly to show you the relevance of caching and distributed memory in a distributed microservices architecture, I'll show you a small demo of how it works. So the thing is, I don't really have here a microservices architecture, but I have one service. And this one service provides a list of, in this case, it's a list of schedules, but it doesn't matter because you will only see JSON out of it. So I'm sorry I don't have better visualized demo, but the service provides some JSON data, and the thing which we want to do is to scale this one service into multiple instances and still have all the data available, and also take advantage of caching the data, so that when one service gets data from outside, it can put it into distributed memory, so that when you call not only that service but also another instance of the same service, you get the data much faster than it would be if it had to go to another service and request the data again. So so this is just the application. It's all what I have. When I press this, I have to wait a bit because I simulated slow access to the data, either from database or from external service, and as a result, I have some JSON. Not interesting. But what is interesting is how I can easily speed up the service. And I don't remember now if I already applied caching. No. So I have to go into code and go into the resource, and here is the method that is called to get the data. It calls another object that retrieves the data from somewhere, but we can easily cache the data of this method just by one line of code with the JCache API, which is cache results or cache what is the name? Yeah, cache results. That's one part. Another part is that the Hazelcast is used behind the scene to cache the data, and Hazelcast is distributed, so it requires every data cached to be serializable. And there's one problem in this response return type. There is no guarantee that the response from JAX-RS is serializable, and in fact it's not, so it would fail. What I need to do is to change it a bit and basically simplify to get around with response and just return what I have, and let Jaxares convert it to JSON behind the scenes. So I'll just what did I have? I'll just return the entity and avoid converting it to a Jaxares object, which is not serializable, but I will return the entities which are, and only afterwards Jaxares will convert it to JSON. So once I return a serializable result, I can apply cache result, and now I think it already deployed. Uncompilable source codes. What did I miss? Return. So now the first request takes the same time as before, but let me copy it to another window. It's instant when I repeat the request. And this is just by one annotation. It allows distribute the data or cache the data. We're not still distributed because we have only one service. But if we start another service that connects to the Hazelcast cluster, and listens to another port, I'll just change 8080 to 8081, and I hope still not there. What's happening? Oh. Well, something went horribly wrong. Okay, I'll see if it fixes, but if the demo was working, I will get the data almost as fast as in the second time I access the data, and the difference would be only that the data would need to be copied from the first instance, and actually it would need to be copied only when if it's not available. And in this time I would have two instances, and both of them would share the same data, because Hazelcast, what it does, it also replicates the data to ensure that everything works, even if some services are dropped from the cluster. So when I have two services and replication set to have at least one replica, there's always one replica at both services. So I'll see if it runs. But unfortunately, we don't have so much time, so maybe later. And now I want to show the possibilities when you introduce data grids in your application, how you can scale your application. So first thing, you can add additional instances, which I just did. I added instances, they share the same data if we put the data into the distributed data grid or into JCache. But we can also configure the data grid so that, no, that's another step. In this step, we can add more nodes to the cluster without running our application. If we just don't want to scale our service, but we want to scale the memory, so we will just run, in this case, another instance of Payara Micro, which joins the cluster on a different system, has the memory of the different system and contributes the memory to the shared distributed structure. And what happens is that some parts of some replicas from existing members in the cluster get moved away, freeing memory in these nodes and filling memory on the newly added node. So you don't have to always run your application again and again if you don't want to scale the application, the service, but you can, as an alternative, only scale the memory. So what we did, or what we would do, is start multiple instances of Payara server or Payara Micro. It doesn't matter in terms of scaling. What we normally do is put load balancer in front of them so that the clients don't have to know where to ask for data and which node is up and running or which is down. So they always have one address, one endpoint, which load balances to any of the live nodes. And then we also need to may scale memory by adding multiple nodes, but without our application. So we don't need to think about configuration or how the new nodes will integrate with other services. They will add just more memory. And this is just by spawning a new node. You don't need to configure anything. The third step you can do is to separate the data from your application. So first we had a service that used the JVM to run the application, to run the code, and also save the data. Then we allowed to move some data to somewhere else, and now we can configure our service to not save the data and move all the data away so that it doesn't fill the heap. And this makes sense if you, in one case, when we have want to have high throughput nodes which are not affected by additional garbage collection. So we want to keep the amount of used memory to minimum and move all the memory out to other nodes. Important thing is to realize that when we have a cluster, it's not only the JVM doesn't store only memory used by our application, but it can be also if other services join the same cluster, other services may offload memory to another service's heap. So if we are afraid that could affect or degrade performance, we could avoid having the shared data in some critical services, and then everything would still work. It's just the data would not be there, but always the service would have to ask the cluster. So the performance would be a bit slower if the service accesses the data, but then if it needs to do some computation fast, it will be fast because there will be less garbage collection. Another use case where you can use this pattern is when you have limited amount of memory on your devices. So if you want to create a cluster across Raspberry Pi or some embedded devices and also have some nodes which are bigger devices and make them communicate to each other. So the bigger devices could be proper nodes having the data, and the smaller devices would work in the same way without any tweaks to our application. They would just not store the memory, keeping the amount of memory used low. So this is how it looks like if we scale memory and scale and offload memory from some services to the other services by making the most critical or embedded or services running on small embedded devices. In Hazelcast it's called light nodes, so we turn them into light nodes, which means it works in the same way as all the other nodes. It just doesn't keep the data, so it has to always have to check another service and get data from it, or most of the time not only one instance, but it gets data from the cluster, so from anywhere it's available. And Hazelcast is intelligent enough to know fast where the data is available, so it doesn't ask every node in the cluster. It has sophisticated algorithms and does it pretty efficiently. Oh. So the next step would be, if we want to granularly scale and we have more microservices, or we have a bigger microservice which we want to split and separate into smaller microservices. So that's where Payara Micro, because it's a bit more micro, fits. You can just take some pieces of your application, put it on Payara Micro, and scale it up independently from the rest of the code. So it's very similar. But when you scale services like this, you still need some proxy when you access them with the REST interface. So another part of distributed data grids fits here, which is distributing information actively, not just passively, like storing and when somebody needs it. But data grids have topics and other communication mechanisms, so you can actively notify other nodes, and you can use this data grids as even bus, which is already there. You just have to use it because all the services are connected already, and it would be just a pity not to use this communication mechanism and use only the memory. And this brings some advantage over the REST communication. One of it is you get rid of additional thing you need to configure, which is a load balancer or a domain name server or anything, or some load balancer on the client side, because you just send the message to the cluster, and then any node in the cluster will receive the message. Obviously, you have to design your application to be message driven and not waiting for the response actively. So this is not always the best option, but message driven applications, coming back to the Reactive manifesto, are the future. When you want to really build scalable applications, you should always consider message-driven communication, because it's more superior and much better scalable than request-response communication. Okay, so I'll check if the demo works. I don't know. I'll try to run it directly like this. For some reason, port 81. Do you have any questions? Has anybody used distributed data grids, Hazelcast, or anything similar, infinite span? No. Well, what is your experience? Are you happy to use it in the future? Well, I hope so. Like, it's, yeah.
Overall, yes.
Yeah.
So it's a bit complex because it's a cluster, so you have to be careful in production.
Yes, yes. It poses some challenges. Like, one of the not so obvious challenges is that when you have auto discovery of the cluster, you have to be careful you don't connect to a cluster that you don't want to connect to, because sometimes it happens that you may run a test cluster and it runs on the same network as production cluster, and you may easily connect to the production cluster. But there are ways to avoid it, like create a password, somehow differentiate between these clusters. Okay, so I was able to run the application. I think no, I'm not going to fool you with the demo. It's playing tricks on me. So if you don't have any more questions, just enjoy the rest of the conference, and come to take some t-shirts if you want.